Okay.
Yes, ma'am.
Okay. So this equation is actually for describing the wave motion again. In the last class we were talking only about the simple harmonic motion part. So today we will be applying this linear wave equation for all kind of waves which are exhibiting in nature. Okay. So a wave function in this is only dependent on two variables, space variable and time variable. And if we are considering the one-dimensional motion of wave, so we have considered wave function as y as a function of x and t, where x is a displacement along x-axis and t is the time. Okay. So once we get this equation, we can say that okay, we have got the solution of the linear wave equation like we were solving in the earlier lectures also. Okay. So it will be giving you why we are trying to devise a linear wave equation, because we will be able to find the other wave parameters also after finding out this particular wave equation, because we know velocity is dy by dt, again acceleration is dv by dt. So once we get the value of this particular y wave function, then we can get the other values also easily. Aditya Rohila is from your class? Okay. So linear wave equation is basic to many forms of wave motion. That is the reason we want to devise this equation. As you can see here, we are discussing the motion along x-axis. V is the velocity, lambda is the wavelength, and y naught is the, you can say, the maximum amplitude of this particular wave motion. So we are considering a string, a part of this particular string, which is given a motion by this particular hand. So we are considering any part of it like this. Let it the distance be dx. So the tension will be created on both the sides, which is being marked by t vector. Okay. And then we are considering a small element of this particular string delta x, which is having a mass, small mass dm, or you can say the mass is mu or dm, anything. Now what we are going to do, we have to again get the equation of motion like we were doing in the previous derivation. We want to devise or get the equation of motion here. Now equation of motion will again be given by balancing all the forces. We need to balance all the forces, and we are trying to find it along the y-axis, that is the vertical force exhibited on this particular string, because we are considering that its equilibrium position is along the x-axis. Okay, the equilibrium position of this particular wave which is generated in the string is considered along x-axis. So we will be calculating net force acting on this string element in the vertical direction, that is y-axis. So end of the element is making small angles A and B with the x-axis. So with the x-axis, if we try to make the angles, theta A angle at point A and theta B angle at point B. Now what are these points A and B? This point A is at, you can say, position x along x-axis, and point B is at x plus delta x, because we are considering this much amount of string element. So point A and point B are at different positions, and we are trying to find out the force on these particular points. So net vertical force, or you can say all the like summation of all the vertical force, is equal to tension multiplied by sine theta b, because vertical component sine, this is the vertical component for A point, and vertical component for B point. Y axis resolve, if you resolve it along y axis. Okay.
ये 11th में पढ़ा था.
हाँ, that is the same, but we have to do because it is there in your syllabus. Okay. So जिन्होंने, those who have already read, please, it will be like a revision for you, and those who haven't done, it will be a lecture for them. Okay. But we have to cover this topic. It is there in your textbooks also, and we need to do this, and it is important from exam point of view. Okay.
Okay.
It is there. Like what happens in the first year of engineering syllabus, many things are getting repeated from 11th and 12th syllabus. But here we will understand the applications also. While doing some numericals, you will get to understand its applications also, how this is actually important, these equations. Okay, like in the last class, we discussed about the simple superposition principle. And did you guys already know that the superposition principle is for controlling the volume? You were knowing that? So after every equation, we will be applying it like where it is actually used in the day-to-day applications. Okay.
Ma'am, it is used in noise cancellation.
Sorry, noise cancellation. What? Yes, noise.
Ma'am,
I got it. Yes, yes. This is also used in noise cancellation. Exactly. Right, right.
interference of it.
Yes, 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 yes. These are normally there are in now your in your AirPods, or like many Bluetooth-based devices are having this noise cancellation property. Okay. So the net force along the vertical axis is given by T sin theta B minus T sin theta A. Once you take it T as a common, then sin theta B minus sin theta A. And now considering your mathematics, that is a small angle approximation. We can consider the angle is very small. Sin theta is equal to theta, or you can it is also comparable to a tan theta part. So we have just used a small angle approximation here in this equation and transformed our equation to this is equation number 1, this will be equation number 2. So from equation 1 only, by applying the small angle approximation, we have reached to equation number 2. Okay. So Fy is almost equal to approximately equal to tension times tan theta B minus tan of theta A. Now we know that like when we plot some graph, the slope is given by again delta y upon delta x, and this is also given by tan theta A, right? Tan theta. Slope is the change in y value upon change in x value, and this is also depicted by the tan of some angle. So we can apply this particular rule out here, and our equation will change to this particular value, t times del y by del x at point B, because point B was coming before, and then del y by del x at point A. Now why we are taking partial derivative here? Anyone who can answer?
Because we are dealing with subatomic particles inside.
No, no.
And there is small. Ma'am, at an instant.
Yes.
Yes, ma'am. We are dealing with a small angle.
No, not small angle.
Then we are using it to a particular time.
Yes, we are using it at a particular time, and y is a function of two variables, x and t. Partial differentiation comes into role when you are considering only one variable. You are not taking the two variables, because y is dependent on two quantities and you are differentiating it partially, not fully. If you say del y by del x, it will be partial if you are doing along time domain. Then again it will be a del y by del t. Getting my point? So partial.
Two independent variables.
Yes, right. Okay. So now we have got the answer also. So we will write the partial differentiation of del y by del x along point B and point A. As simple as that. So we have arrived at equation number 3 here. Here we have stopped now. Now we will be working with some new method. Okay. We are using Newton's second law. Force is equal to mass into acceleration. Okay. Acceleration will be produced along the y-axis, m times ay. Now also, I told you mu is the mass per unit length. So total mass of the string can be calculated by mass per unit length mu times delta x. The total mass of that particular element which we have taken will be mu times delta x. So we can say F is actually equal to mu times delta x times of acceleration y. Now again, we know that acceleration is given by dv by dt. Again, v is actually equal to dx by dt. But the motion is along, like we can say, it is actually, we are considering the time domain only now again. Okay. So what we used to do, we used to differentiate that wave function to get velocity dy by dt. So it will be d2y by dt square. But we cannot take full derivation. We will take again partial differentiation. Why? Again, y is a function of both space and time variable. You are considering only one variable here. So again, the partial differential will come here. So you have got the fourth equation. Any doubt till now? Okay.
No, ma'am.
So let's proceed on equating the two equations as 3 is equal to 4. On equating the two equations, you get this particular equation. Mu delta x del 2y by del t square is equal to t times del y by del x at point B minus del y by del x at point A. On rearranging it, once you rearrange this equation, mu upon t del 2y by del t square del y by del x times at point B minus del y by del x at point A upon delta x. Now this equation we have already read somewhere, not of this type but of this type. When we used to study about a differentiation form, how it can be represented in limits. Okay, like differentiation of this particular term is also equal to limit delta x tends to 0 f x plus delta x function at, this is the point x, this is the point x plus delta x, and distance is delta x which you are considering. So differentiation can also be found by fx plus delta x minus fx upon delta x, right? This is the formula in your maths also, which you see. when limit delta x is very very small, delta x is tending to 0, this length element is very very small. Okay, so del f by del x can be represented in this particular form. So by using this particular formula, okay, by using this particular expression of your partial derivative, we can write this function as del 2y upon del x square. Is it clear why we are writing this function as del 2y by del x square? ये कैसे आया?
Yes, ma'am.
What is happening? Here it's a complete function, f function, right? Once you are getting its value, it is coming out to be first derivative of this function. But here in this equation, already first derivative is here, f dash is there. So you will get the second derivative, one more derivative of this particular function which is written on the right hand side. So that is why it is coming out the second order derivative. Getting my point? Why where we have written single order derivative, first order derivative, and here we have written double order, second order derivative.
Ma'am, एक बार ये वापस explain कर दीजिए.
बिल्कुल. So what is happening? Is this clear? Have you read this before? This particular expression in your
Yes, ma'am.
differentiation? Yeah. So
Yes, ma'am.
we are yes, okay. So what we are doing is we are using this particular expression to solve the right hand side of equation 16.25. Okay. So
Okay.
yes. So what we are going to do? Okay. So del y by del x. So here what is happening? F x plus delta x is actually point B. देखो यहाँ पे ये point B है, x plus delta x.
Yes, ma'am.
And f x हमारा point A है. ये clear है? ये f x
Yes,
हो
ma'am.
गया, ये f x plus delta x हो गया. अब ये ध्यान रखना, ठीक है? So
Yes, ma'am.
what is happening here? हमने इसको लिया, it is actually point B. तो हम लेते हैं इसको f dash at point B because यहाँ पे we have a first order derivative, ठीक है? Minus f dash a, यहाँ पर है minus f of x because B is x plus delta x, a is x upon delta x, again we are considering delta x. So जब we are having this expression equal to first derivative of partial derivative of with respect to x, because we are not taking time, del f by del x. So what will happen with this particular term? We will be taking second order derivative for this. So यहाँ पे क्या हुआ? Del 2y by del x square. F actually function is actually represented, wave function is represented in the form y as a function of x and t. So that is why we are taking del 2y as a function of x and t upon del x square on the right hand side. Getting my point? This is
Yes,
how,
ma'am.
yeah, this is how we have got this particular expression. This is called as the final linear wave equation for the wave traveling on a string. Okay,
Yes, ma'am.
we can represent it in another very good in other form also. So let us see that. So so from here we can get del 2y by del x square is equal to 1 upon v square del 2y by del t square. But how come mu by t, here mu by t is represented as 1 by v square? Mu by t is represented as 1 by v square. So let's get this formula first, okay? So y is representing the vertical position of element of string, okay? And this is about traveling wave because it is changing, displacement is changing with time, okay? So let us try to solve this particular. How have we put the mu by t? Mu is the mass per unit length upon tension value equal to 1 upon velocity square. Okay. So this is again the linear equation, linear wave equation in general format. Okay. And if we talk about the light wave, what will happen? V will be replaced by C term, where C is the for light wave. If we talk about photons or light wave, so this wave equation can be written as del 2y by del x square is equal to 1 by c square del 2y upon del t square. Okay, so let us see how we can write this equation equal to mu by t equal to 1 is equal to 1 by v square. So we were having this displacement equation जो हमने निकाली थी after using the superposition principle, a sin kx minus omega t. This is a general solution of equation, wave equation. You differentiate with respect to time del y by del t, it will be minus omega keeping x constant. Okay, that is why partial differentiation again minus omega a cos kx minus omega t If you differentiate it one more time, it will be minus omega square a sine kx minus omega t. You have got this particular term. Del 2y by del t square is equal to minus omega square a sine kx minus omega t. Okay. Now you differentiate with respect to x, keeping t as a constant. So you will get del y by del x ka cos kx minus omega t and del 2y by del x square minus k square a sine kx minus omega t. You have got equation number A, equation A, del 2y by del t square 1 and equation B, del 2y by del x square 1. Right? Now divide the both, divide two equations. So what will happen? It will come in the format, yes. Once you get this equation, what we are going to do? We are going to divide. This is equation A again. This is equation B again. Let's divide this equation. What you will get? Del 2y by del t square upon del 2y by del x square is the here it will come minus k square a sine kx minus omega t. So sine kx minus omega t will cut with sine kx minus omega t. A will be cancelled with a. So in the end, what you will be getting? Del 2y by del t square is actually coming out to be equal to minus k square, minus minus will get cancelled out, so plus k square upon omega square times del 2y by del x square. So what is the value of omega by k? Omega by k is actually v, wave speed. So we can write it as del 2y upon del t square is equal to 1 by v square del 2y by del x square, right? So this
Yes,
is,
ma'am.
yeah.
So
So,
not del 2x.
sorry, this is x.
Ma'am, del 2y should be del 2x.
Del 2y should be del 2x, no?
मैम वो डिवाइड कर रहे हैं ना ऊपर.
हाँ जी, we are dividing it.
तो हम d2y कट नहीं जाएगा.
d2y, why it will get cut down? This is differentiation with respect to time variable t. This is differentiation with respect to time variable x. We cannot cut it like this, del 2y by del 2y. No, it is not happening in maths, okay? This is an operator. Your del, this is an,
Not cancelled.
yes, this is operator. Once it's okay. You ask questions, okay? It is actually an operator like subtraction, addition. This cannot get cut anytime. It cannot be cut, okay? It's like your addition, subtraction, division operator only. In differentiation, it's called differential operator. I told you, okay, before also. It's your differentiation operator. Operator cannot be cut at any time, okay? So you got this equation number B here. And if we refer the previous equation, del 2y by del t square is equal to t upon mu del 2y by del x square, and compare with this equation del 2y by del t square 1 by v square del 2y by del x square. So from here only we are able to get that this formula, that actually our v is equal to under root t by mu. Getting my point? Wave speed is given by the restoring property, tension property, upon the inertial mass property. Okay.
Yes, ma'am.
So these expressions were very like you can say important for your numericals point of view, and also for derivation part you have already done as you were telling me, but yes, we had to do it again, so I made you revise it. Is there any question from anything which I have taught you just now? Yes, is there any question you want to ask class?
No.
Okay, that's great. So I am going to give you some questions to solve. Just hold on.